Okay, so suggest why the coil turns when a current flows. So as the current flows through the coil, it creates a magnetic field around the coil. So current creates magnetic field around coil, which interacts, and that's our key word, we always talk about for the motor effect, the interaction between the magnetic field around the coil and the permanent magnetic field, which is between the north and the south pole. So the current creates a magnetic field around coil which interacts with the permanent magnetic field, permanent magnet, and that exerts a force on the wire or the coil. Okay. State the name of the rule that you use to work this out. So in the next part, we're going to work out what direction this coil is going to turn. Okay. So first of all, in order to work this out, we're going to use Fleming's left-hand rule. Okay. So that's the rule we're going to use. And to work out the direction, what we need to do is just remember, I'm just going to put my camera up a bit, remember what the three things mean. So first of all, we're using our left hand and we need to arrange it like this. So the thumb is up, the first finger points forward, and then the middle finger is at 90 degrees, like that. Okay? So the thumb is going to represent the motion or the force, so that's kind of the answer. That's going to help us to work out which way the coil is rotating, and we need to align our first finger for the magnetic field of the permanent magnet and the second finger for the current in the wire in the right directions. So if we look at the left hand side of the coil, the current is coming out of the page kind of towards us, so I'm going to put my middle finger going that way, and then the field between the permanent magnets runs from the north to the south. Okay, so in this case that's right to left. So my first finger is running from towards the south pole, basically. So my middle finger is sort of going towards me out the page. My first finger is going from north to south, and then that leaves me with my thumb. Okay, so my thumb is pointing up. So that means on this side of the coil there's an upwards force. Okay. On the other side of the coil, the field's still going north to south, so left to right, but the current is going into the page on this side of the coil because it's sort of going round, looping round and coming back out again. So in order to see what happens with the force here, I need to twist my wrist round sort of 180 degrees, so my middle finger is now going into the page. My first finger is still going towards the south pole, and now my thumb is pointing down. Okay, so this side of the wire is going to go down. So if the left side is going up and the right side is going down, it's on the sort of an axle here so it can rotate. What's going to happen? It's going to rotate round like this. Okay, so in order to give that a direction, we call that clockwise because it's going round the same way the hands of a clock would. So the direction is clockwise. And for rotations, we always talk about rotation as being either clockwise or anti-clockwise. And the other place we see rotations is when we're doing moments. Okay, suggest two ways in which the size of the force on the coil could be increased. Well, there's more than two ways you could do this, so let's put them all down. So we could either increase the current in the coil, Or we could increase the number of coils. So the more times you coil round this loop, the greater the force on the coil is going to be. We could also increase the strength of our magnet here. It's really important that you don't say increase the size of the magnet. We don't want to talk about having a bigger magnet. We want to talk about having a stronger magnet. Okay, so increase the strength of the permanent magnet. Okay, that's that one.